Hi, my name is Dinesh Kanda Izhar, match numbers of B014200007.
Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Haris Najmi bin Muhammad Rosli. Metric number B0419200004.
Saya Asal Masri bin Abdul Samad dan nombor metriknya B0419200021.
Hello guys, a very good morning. My name is Yang Chi-Yong and my metric number is B0419200041.
So today we want to talk and present about vector calculus, the introduction of the Grimm's theory. And now we talk who's the creator of the Grimm's theory. So Grimm's theory was created by George Grimm. George Grimm was a British mathematical physicist who wrote an essay on the application of mathematical analysis to the theories of electricity and magnetism in 1828. The essay introduced several important concepts, among them a theorem similar to the modern Grimm's theorem, the idea of potential function as currently used in physics, and the concept of what are now called Grimm's function. Grimm was the first person to create a mathematical theory of electricity and mechanism, and his theory form was foundation for the work of other scientists such as James Clerk Maxwell, William Thomson, and others. His works on potential theory ran parallel to that of Carl Friedrich Gauss. So the behind idea of this theorem is we can assume that when C is an oriented simple closed curve, the integral represents the circulation of F around C. If F were the velocity field of water flow, for example, this integral would indicate how much the water tends to circulate around the path in the direction of its orientation. One way to compute this circulation is, of course, to compute the line integral directly. But if our line integral happen to be in two dimensions, for example, F is two-dimensional vector field and C is a closed path that live in the plane, then Grimm's theorem applies, and we can use Grimm's theorem as an alternative way to calculate the line integral. Grimm's theorem transforms the line integral around C into a double integral over the region inside C. However, it's not obvious what function we should integrate over the region inside C so that we still get the same answer as the line integral. The notion of circulation can aid us in determining what this function should be. Think of the integral f as the macroscopic circulation of the vector field f around the path C. Now imagine you cannot reach a microscopic version of circulation around a curve. This microscopic circulation at point xy has to tell you how much f will circulate around a tiny closed curve centered around xy. We could picture the microscopic circulation as a bunch of a small closed curve shown below in green, where each curve represents the tendency for the vector field to circulate at a location. Imagine that the small curve were really small, really small, much smaller than the picture. Grimm's theorem is simply a relationship between the macroscopic circulation around the curve C and the sum of all the microscopic circulation that is inside C. If C is a simple closed curve in the plane, remember we are talking about two-dimensional, then it's around some region D, shown in red in the plane D, is the interior of the curve C.
Next, I would like to continue the presentation, and I would like to talk about the idea behind the Grimm theorems. The Grimm theorem said that if you add up all the microscopic circulation inside C, for example the microscopic circulation in D, is total exactly the same as the macroscopic circulation around C. The region below show that by adding up all the microscopic circulation in D means taking the double integral of the microscopic circulation over D. Therefore, we can write the formula of Green theorem as integral f ds equal double integral of microscopic circulation of f dA. Now, what is the microscopic circulation? The microscopic circulation of Green theorem is the same as the microscopic circulation of the curl of a three-dimensional vector field. The only difference is the Green theorems apply only with two-dimensional vector field, for example, the vector field in the xy plane. The microscopic circulation that we want is the circulation in the xy plane. Besides, the microscopic circulation in the xy plane turns out to be the z component of the curl. As you can see the following direction of the curl and the definition of its component is determined by the right-hand rule. Imagine that by curling the fingers of your right hand around the circles, indicating the circulation, one represents such circulation by the vector pointing in the direction of your thumb. In three dimensions, point the thumb of your right hand in the positive z direction. Then, the fingers of your right hand curl in the counterclockwise direction parallel to the xy plane. So, we can know that the right-hand rule said that the circulation inside the xy plane should corresponding to the z component of the curve. So, we can conclude that the formula for the Green theorem is the microscopic circulation equal curl Fk, where the k is the unit vector in the z direction, and we can write the Green theorem as integrate f ds equal double integrate curl f k dA. Besides, the component of the curl inside the z direction is given by the formula curl fk equal derivative f2 over derivative x minus derivative f1 over derivative y. The z component of the curl is offered term in the scalar curl of the two-dimensional vector field. You can get the intuition behind this formula or see how to derive this formula from the definition of the curl. By using this formula, we can write the Green theorem as integrate f ds equal double integral bracket derivative f2 over derivative x minus derivative f1 over derivative y bracket dA. So, to make sure that the Green theorem gives the right answer, we need to be careful that how we arrange the curve C. The right-hand rule says that curl Fk corresponds to the amount of circulation in the counterclockwise direction. Hence, the Green theorem, as we have written, is only valid for the curve oriented counterclockwise as the picture shows above. In this case, we can say that C is a positively oriented boundary of the region D. The one way to remember that what positively oriented means the following. For example, if you were walking along C in a positive orientation, the region D will be on your left. If you mess up the orientation, you will be off by a minus sign. Next, I would like to pass to the slide to Asa Fansuri.
Thank you, Yong, for giving me a chance to present. I will explain the application of Green theorem. Green theorem provides another way to calculate this equation, which is integral C f multiply ds, that you can use instead of calculating the line integral directly. However, some common mistakes involve using Green theorem to attempt to calculate line integral where it doesn't even apply. First, Green theorem works only for the case where C is a simple closed curve. If C is an open curve, please don't even think about using Green theorem. If you think of the idea of Green theorem in terms of circulation, you won't make this mistake. Green theorem convert the line integral to a double integral of a microscopic circulation. The double integral is taken over the region D inside the path. Only closed paths have a region D inside them. The idea of circulation makes sense only for closed paths, and the line integral represents circulation around the region only if it's simple. So if you ask to compute the integral, you are using this equation, integral c y ds plus sy dy, where is c is the line from 0, 1 to 1, 1. Can you use Green theorem? No, because c is open curve. You could, for example, use Green theorem to compute same equation, but where c is the counterclockwise unit circle. Yes, we can use Green theorems. Second, Green theorem can use only for vector field in 2 dimensions, such as f sy equal y sy. It cannot be used for vector field in 3 dimensions, s, y, z. So don't bother with Green theorem if you are given to as integral like this equation. Integral c z ds plus sy dy minus yz dz. Because why? This equation is a 3-dimensional, even if c is closed path.
Alright, let's continue with the last part of the presentation, which is question of Green's theorem. So the first question is, use Green's theorem to evaluate integration of c xy dx plus x squared y cubed dy, where c is the triangle with vertices at 0, 0, 1, 0 and 1, 2 with positive orientation. So, the solution for question 1, first of all, we must identify which one is P and which one is Q. So, firstly, the P is xy and the Q is x squared y cubed. And then, the value of P differentiate with y will give us x, and for q, differentiate q with respect to x will give us 2xy cubed. Alright, from the graph we can see that this is a triangle with the slope is equals to y equals to 2x, and as you know, Green theorem is a double integral, so we must first know what is the limit for the two integral of dy and dx. So after we know about the limits for y, it is from 0 to 2x, and for x is 0 to 1. Substitute dp over dy and dq over dx into the formula with the limit that we already find earlier, and then firstly we integrate with respect to y, which will gives us xy power of 4 over 2 minus xy, and then we substitute the limit value into the equations, which gives us 8x power of 6 over 6 minus 2x square dx, and then we integrate with respect to x, which will gives us 4x power of 6 over 3 minus 2x cubed over 3, and lastly substitute the limit for x, which is 0 and 1, which will give us final answer of 2 over 3. And second and the last question for Green theorem is use Green theorem to evaluate integration of c y cubed dx minus x cubed dy, where c is the positively oriented circle of radius 2 centered at the origin. So this is the solution for question 2. First, we must know what is P and what is Q. So for this question, P is y cube and Q is negative x cube. And then differentiate P with respect to y will give us 3y square, and also differentiate Q with respect to x will give us negative 3x square. As you know from the question, it is said that this question is a circle with radius 2, so we can already know what is the limit for dr and d theta. So when we use circle, we change the dy dx or dx dy into r dr d theta or r d theta dr. So for the limit for dr is 0 to 2, and for limit for d theta is 0 to 2 pi. Okay, first we substitute dp over dy and dq over dx into the formula, and write down also the limit for dr d theta. So it will give us negative 3x square plus y square r dr d theta. As you know, x square y square is also equals to r square. We simplify the equation, it will give us negative 3r cubed dr d theta, with r limit is 0 to and theta limit is 0 to 2 pi. Then we integrate the value of r3, which will give us r4 over 4, and then we substitute the limit for r, which is 2, 0 and 2, which will give us the value of 4. After that, we integrate it with theta, which will give us 4 pi with the limit of 0 to 2 pi, and then substitute the limit into the equation, and lastly it will get negative 24 pi as the final answer.